Good morning. Good morning. All right. Yes. Good morning. Good morning, Melanie, who I saw bright and early. Good morning, Vicky, who I see in animation. Good morning, Benita, who I see in both avatar and in chat, which I appreciate. Good morning, Vicky, who I also see in the chat. Good morning, Melanie, whom I now see in the chat, and who again was super prompt, noticed, appreciated. Good morning, Amelia. And good morning, Hudson. Okay, there's more. Good morning, good morning. Okay. Did I say Hudson? Yes, good morning, Hudson. Good morning, Amelia. Good morning, everybody. Okay. We will there's Vincent with the what's sort of shocking about Vincent's avatar is how, in a way, not distracting it is. I mean, it should be really. It's sort of just alluring, though. There's something about it that calms my soul. I don't know. Anyway, okay. And that takes a lot of work. Okay. So good morning, Vincent. And good morning, everybody. Okay. Oh, good morning. Yes. Okay. So we're gonna get straight back to physics, to Newton's laws. Again, where I am right now. Hello. Oh yeah, there's a lot of okay, here we go. Here we go. Okay. Yes. I want to keep just talking about I want to just keep analyzing the situation of the apple on the table that got prompted by the homework problem. Um, but again, I want to expand this homework problem once we've done the basics to sort of show you how it eventually applies to any kind of problem, force problem, particularly your lab number 5. So, I'm just looking to say, okay, yeah. So again, I mean, I hope it's clear. Well, to be clear, I'm going to do this quick. Good morning, Gabriel. Thank you. To be clear, where I am again is right here, right? This is where we were yesterday. Um, where we left off yesterday was at drawing what it says an FBD. Actually, I would say, strictly speaking, what we were drawing yesterday was a pure FBD, a pure free body diagram. Um, what we're going to see by the end of today, or what you see in your lab, is there's yet another kind of picture that becomes vital for doing the math of these problems, and that that third type of picture is the component free body diagram. Okay, now sometimes it's not necessary. In fact, in this case, it won't be necessary. But I do want to make clear just one last before going any further. In general, with these force diagrams, there's system schema, pure free body diagrams, and then component free body diagrams. And it's ultimately the component free body diagrams that enable us to set up all of the math for the left side of F net equals MA. It's ultimately, when things are complicated enough, as in the lab number 5, it's ultimately the purpose of the system schema is to make a pure free body diagram. The purpose of the pure free body diagram is to have something to break up into vector components and thereby make the component free body diagram. And it's the components that you end up adding up and putting on the left side of Newton's second law, one axis at a time, to solve any kind of complicated force problem, such as the lab. So, um, so that's like the goal of all of this. Now, so what I'm going to do now, though, is I'm picking up on where I was yesterday. Yet, I'm going to switch the screen in a second. So, whatever screenshot or just like me, we're in the middle of this multi-force warm-ups problem. Where we were yesterday was draw a pure free body diagram of the apple. And then it asks this thing about Newton's third law pair, which is what I want to well, I want to finish the problem now and then like add features to it to make it more and more like your lab situation. Um, so okay. Um, so I'm going to switch screen. So I'm going to go switch screens back to where we were yesterday. Okay. No, I'm not. I, I, oh my God. I'm sorry. Okay. 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 I'm just looking right. So we're back. So the apple sitting at rest on the table. The pure free body diagram looks like this. This is where we were yesterday. That is the pure free body diagram. We have two forces acting on this apple. We have one downward force of weight, the gravitational force from the earth, which is always there, is always pointing downward in every single diagram from now on, right? And always abbreviated or labeled mg in every single diagram. Again, mg is the force of gravitational attraction exerted by all of planet Earth or the center of planet Earth, if you like. And it's always, again, well, I guess it asks us later in the problem, but it's mg is the right. M is mass measured in kilograms. G is acceleration that would occur during free fall measured in meters per second squared. And kilograms times meters per second squared gives you a force measured in newtons, which is the force of gravity. All right, I'm over. Okay. That's pulling down. That's in every single diagram. Then we've got this upward force that we from here on in calling the normal force from the table. It's it's pushing up on the apple. How do I know it's there? Because the table is an object that is touching the apple. And it's touching it from underneath, shoving it upward. Um, Again, I want to reinforce, like, yes, this is the diagram of the apple sitting on the table. Of course, but once we tilt this table and make the table rough and add friction, then it becomes the lab. So more arrows will get added into this diagram, right? And in fact, some of these arrows will tilt. Right? But this is the basics first of an object just sitting on a table. And the thing I'm trying to emphasize now is that that normal force is there only because there is a surface pushing against the bottom surface of the apple. Like, again, just before I go on, just please understand that just because you have, like, in every single diagram, there is mg. Definitely. You can take that to the bank. But you should not assume or believe that in every single diagram, there is a normal force. Normal does not mean it's normally there. And normal doesn't have anything itself to do directly with gravity. In fact, okay, I'm going to move on now to, okay, so I'll say more about that in a minute. But so this is the diagram. You got the upward force of the table pushing the apple. You got the downward pull of planet Earth pulling the apple. That's the pure free body diagram. Then the question asks, yeah, it says, this homework 8. Oh, excuse me. Sorry. This is homework 8. Okay. So then it asks in 4. What are the Newton's third law pairs? Now this is English. This is not numbers now, but this is super important. This is kind of a different way of getting at what I was just yelling about a second ago. Like you see these two forces in here. They are in this diagram. They are opposite in direction. And it might even look as though they're equal in magnitude. In fact, they actually are equal in magnitude. But the big mistake, huge common misconception, is to look at those two forces and think, oh, I guess that's what Newton's third law is all about. Like for every action, there's an equal and opposite reaction. There it is. There's an action and there's a reaction. People tend to think that, and it's real and it's wrong. And it's really important to not think that, because if you look at these two forces and you look at this diagram, if you even unconsciously start to think, oh, that's an action and a reaction. The problem, there's many problems with thinking that. One problem is that then you're liable to think, if it's a law, you'd be liable to think, oh, well, whenever there's the action of gravity, there must always be a reaction of a normal force. Like tons of people, and that is wrong. Okay, I'm getting myself all. So the question here, is, wait, what does this have to do with Newton's third law? Like, how does Newton's third law like apply to this situation? Is there action reaction going on? Well, yes, there is action reaction going on. There's always whenever there's action, there's reaction. But the important thing is to realize what the actions and the reactions are. So here's the deal: Newton's third law, the Newton's third law pairs are, you look at each arrow is an action in its own action reaction pair. The reaction, its reaction is in some other free body diagram. This is what I mean. So it says, okay, so each arrow, so every arrow in a free body diagram is an action. In other words, you don't ever see the reactions in a given diagram. No diagram contains action and reaction pairs. The whole idea of action and reaction is that force is a mutual, symmetric interaction between two objects. In other words, where you see the pairs is in your original system schema. That's why in your original system schema, you have lines, not arrows. Notice so I'll show you what I mean. I look at one arrow here. I go one arrow at a time. First, the arrow that's labeled mg, like gravity, weight, right? What's going on there? Well, the action that it's telling us is that the Earth is pulling down on the apple, right? That's what gravity means. The Earth is pulling down on the apple. It's an interaction between two objects, right? That's the action. So what's the reaction to that? The reaction is, well, look at the original system schema. You have a line between the Earth and the apple. The line is trying to get across to you that there's no priority. There's no preference. The apple and the Earth are just in a tug of war together. That's what action reaction is trying to tell us, that if the Earth is pulling down on the apple, then the apple is pulling back up on the Earth. In other words, the apple is pulling up on the Earth. And that is true. That is the case. That is a force that is happening somewhere in the universe. Is that the other arrow in our diagram here? No, it's not in our diagram, because it's a force that's happening to Earth. if you were to draw a diagram of Earth, you would see a gravitational force exerted by the apple in that diagram. But here, the free body diagram is just focused on the apple. Okay, so that's one action reaction pair. Every action, and the other is this: the normal force means that the table is pushing up on the apple, right? So this is a totally different thing. The table just happens to be pushing on the apple, not because of a law, not because the earth made it do that. The earth didn't make it do that. The table didn't have to be there. The apple could have been in free fall. There's no law that says if you're pulled down by the earth, something else has to push you up. If that were the case, nothing would ever move at all. What we're saying is, oh, there happens to be this table pushing up on the apple. Well, and that's called an action, and it's in our picture. Well, if that's true, then, then, um, then the apple must be pushing down on the table. Those are the two action reaction pairs. In other words, if I ever see for every force I see in a diagram, there's a reaction in some other diagram. The number of forces in a free body diagram could be an odd number, but the number of forces in the whole universe is an even number. I don't know if but that's what I'm saying. Last thing about this. Notice like the symmetry of the patterns of the way these are written. Earth pulls down on apple, apple pulls up on earth. It's literally like once you write one down, even if you're not looking at a picture, you literally could write the other one down just by looking at the words. The earth pulls down on the apple, therefore the apple pulls up on the earth. It's tug of war. Similarly, the table pushes up on the apple, therefore the apple pushes down on the earth. It's always the same word in both cases, and it's always a flip of direction. This is what Newton's third law means. Bottom line, why am I even worrying about this? Is what you do, the normal force happens to be opposite in direction and happens to be equal in magnitude to the weight, but they're not. That's not because of Newton's third law. How? I'll just write this. Whoa, whoa. Now, I'm not trying to trick you, and I will move on in a second. I'm not trying to, if you're looking at that diagram and you think the upward force of the table in magnitude equals the downward force of the earth, of the apple's weight, you are correct if you believe that they were equal in magnitude. But what's the reason? Like, are they always? No, they're not always. How do we know in this case that they are? Because of Newton's second law. It's not because of Newton's third law. In this case, how does Newton's second law work? There's a simple, like what I could do is I look at my diagram. So look, the purpose of the diagram of these arrows is that once you have the arrows, you add up all the arrows along a given axis. And when you and that constitutes the sum of the forces. The net force is literally the sum of all of the arrows in a given axis, taking into account plus signs and minus signs. In other words, here you got the normal forces pointing up along a given axis, and you got mg also pointing along that same axis, but they're pointing in opposite directions. The normal force is pointing up. The weight is pointing down. So I give one of them a minus sign. Like if I say that up is positive and down is negative, then the weight gets a negative sign. So N minus mg equals ma, right? This is a simple example of how to use Newton's second law. But we know in this case that the apple is sitting still. So A equals 0, right? So the whole right side equals 0. Therefore, if that's true, the upward force of the table must be perfectly supporting the downward weight of the apple. I'm going to move on in a second, but what I'm trying to say, is the normal force of the table equal to the weight of the apple in magnitude? Yes, it is. How do we know? Newton's second law, not Newton's third law. And if we know it because of Newton's second law, what we're really saying is we know because we know the acceleration is 0 of the apple. In other words, there can be tons of situations where the acceleration of the apple isn't 0, or the thing is on a tilt or something, and then we would have no good reason to believe that the normal force was perfectly supporting the weight of the object, as is the case in the lab, or the case of the duck in the elevator. The whole next problem on the work, which I'm not going over today, but that whole purpose of that whole duck elevator situation is it's a big elaborate example where you have a normal force pointing up, you have a weight pulling down, but they're not equal in magnitude because the duck is accelerating. Okay, anyway, so I'm going to move on. But all right. So now the next question in the homework is right. Compute the force that the entire Earth exerts on the apple through gravity. I mean, we've sort of already done this, but remember, near the surface of the Earth always tries to pull everything regardless of the. All right, so we already sort of talked about this, but what it's asking is what is um the downward force from the entire Earth? And what we've already said is that's mg. The downward force is mg. Because the analysis we gave yesterday. And the reason it's and it's trying to hint and suggest to you that the ways how we figure that out is that is definitely how hard the Earth would have to pull on the apple such that in free fall the apple would accelerate downward at a rate of g. So that's how hard the Earth is always pulling on the apple. All right, we already said it yesterday, but the reason I think it's asking it right now is to make clear that therefore. Okay, wait, let's make this clear. If, say, for example, I lost my. Say that hold on. I lost the correct pen. Where'd it go? 1 second, 1 second. I think it's this one. Okay. just two things I want to make explicit before going on. If that apple had a mass of 2 kilograms, then its weight is 20 newtons. I'm approximating 9.8 to be 10. So just to be clear, if that apple had a mass of 2 kilograms, then its weight would be 20 newtons, which means the whole earth is pulling down on it with a force of 20 newtons, right? But then what I want to be clear about that is then one, the apple pulls up on earth with 20 newtons. First of all, I just want to make clear that this is how serious and true Newton's third law is. If you could picture that the earth is pulling down on the apple with a force of 20 newtons, I mean, again, I'm just making up, not assuming that the apple is a 2 kilogram apple. First of all, that means that the earth is always pulling down on the apple with 20 newtons, whether the apple's falling or not. Right? That's the apple's weight now. It's just always being pulled by the earth with that amount. But that also means that at all times, always, the apple is pulling up on the earth with a force of 20 newtons. Now, you might say, well, wait, why doesn't the earth accelerate up or something like that? Well, first of all, the apple's not the only thing pulling on the earth. There's tons of, right? There's right now, just as we're talking about this, there's my equivalent in China on the other side of the earth is talking about the exact same thing. And there's an apple being pulled toward the earth on the other side of the planet. It's just a silly example, but the fact is, this apple is not the only, and so there's an apple on the other side of the planet pulling the earth back. Not back, but I mean in the opposite direction, right? So first of all, there's tons of things pulling on the earth. Second of all, F net equals ma. Pulling the earth with a force of 20 newtons does it. That's exactly 20 newtons. But the earth is so massive that it would only, even if this were the only apple on the whole earth pulling the earth up, it's pulling it up with a force of 20 newtons, and the whole earth has a mass of like 6.4 times 10 to the 24th kilograms. So F equals ma, if you divide by its whole mass, the acceleration in response would be very, very tiny. So I'm getting off the topic, but I just want to make clear that Newton's third law is not only about opposite directions, but also about equal magnitude. Okay. And then finally, 6, we already did. Like, what is the force, the upward force that the table has to push up? Hold on, I know someone's here. 1 second. Okay. So in this case, if the apple's weight is 20 newtons, then yes, the table is pushing up on the apple with a force of 20 newtons. But in this case, okay, so that, all right. So those are the questions that were being asked in the original homework. That's that homework problem. Now, I'm going to keep going. I'm not going to go to the next problem in the homework. I'm going to keep going and adding layers of sophistication to this situation. Again, even with the goal of trying to make it more and more like your lab. So, excuse me. Um, um, I don't know why. Okay, so what I want to say first, so I'll just read this out loud. What it says, so again, please stop me if you're confused, but I'm now changing the problem. I'm expanding the problem. So I'm going to add this feature. What if someone were pulling this apple, like someone had a string or something, and someone started pulling the apple like at an angle, 30 degrees relative to the horizontal. So they're pulling the apple. So now the apple starts actually sliding, accelerating horizontally across the table. I.e., like what if, so here's the apple, and here's the table, and someone with a string or something is pulling like this, and we'll say, what if like, okay, say, so we got someone pulling this apple with a string, and the string is like at an angle of 30 degrees relative to the horizontal. And so the string exerts a force that we would call tension. And let's say the tension in the string is given as 30 newtons. I'm just making up numbers. And so we're pulling this apple, so the apple starts to accelerate horizontally along the table, like we're pulling it at an angle, let's say. Um, uh, but but that's for our own purposes, for like leverage or whatever. But the apple slides along the table, and we want to know what's the horizontal acceleration of the apple in this case. In other words, right now, what I'm doing is adding the feature of angles. Like, how do you deal with angles in general? So first, I'm adding it this way. So what would we do? So the goal, again, now it's a problem to be solved. The problem to be solved is what is the acceleration of the apple horizontally if now it's being pulled at an angle, in addition to having its own weight and being on a table, right? So very quickly. So first we do a system schema very quickly. And here it is, the system schema. The apple is a dotted circle labeled mass, right? We have the entire Earth. As always, it's always there, and I don't care where I put it in the system schema, because system schema is not about directions or anything like that. So the entire Earth is always there. So there it is in my system schema. Then I ask, what's everything touching the apple? Well, the table is still touching the apple. The table's still there. So I put the table. And the table is a surface that potentially could be rough. So just in case, I put two lines connecting the table, although it still turns out that we're still saying this table is smooth. So we're going to still turn out to not worry about friction yet. But as a precaution, I always put two lines when I have two surfaces pushing against each other. And then now we've got this other object in the situation, which is a rope or a string pulling on the apple. So I put that anywhere I want. I call it a string or a rope. I mean, it's an object, right? And that string or rope, it follows the one touch, one line rule. Like, there's a string touching the apple. It's not a surface pushing, and it's not planet Earth. It's just a normal everyday string. So it is exerting a force on the apple. Okay, so that's my system schema. In other words, all I've done is added one more force to the situation as it already existed. That's a system schema. Then I go to the free body diagram. So first, So my solid circle becomes a dot. And every single one of those lines is now going to become an arrow in my free body diagram. But I'm going to note right away the surfaces are still smooth. Apparently, like no one told me anything about roughness or anything like that. So I can ignore the line for friction, right? I'm not going to turn that into an arrow in this diagram because apparently there is, as yet, there's no friction. Obviously, friction's the next thing I have to put. But so what are my forces? Well, the downward force of gravity is always there. The upward force from the table, the normal force, is still there. Now I've got this string that's pulling that way. So I've got this force called the tension in the string. So this is my diagram now, my free body diagram. Three different forces, right? Now, in fact, let me make one thing clear. One thing I'm just going to tell you right now, I have to start analyzing now. This is already a case. You'll see by the time we do the math, there is no longer any reason to believe that the normal force is equal in magnitude to the gravitational force. Like I'm trying to deliberately not make those arrows the same size. I don't believe they are the same size. I believe you'll see, I believe the normal is smaller in magnitude than the weight. But in any case, that's my free body diagram. This is my pure free body diagram. What do I do now? Remember, I'm now trying to solve a problem. I'm now actually trying to calculate the acceleration of the apple. So the next step, what I want to be able to do is to set up the math. I want to set up F net equals ma, um, one axis at a time, and add up all the F's, divide by m to get the a. But I can't do it yet because this pure free body diagram now has forces going in all kinds of different directions. What I ultimately want is a free body diagram that has one axis for every axis of space. In other words, okay, what we're going to do, well, I'll read this out loud. What it says is, we must now make a component. Oh, wait, there's something in the chat. Hold on, sorry, one sec. Sorry. Sorry. Yeah. The magnitude of the force from the string was given as 30 newtons. And 30 newtons is the answer. And we're going to use that in a minute. I mean, thank you for asking. Just to be clear, I just made that up. Like it's not on the sheet anywhere, but yeah, it's 30 newtons. Good question. So what this says is we must now make a component free body diagram from our pure free body diagram. How are we going to do that? We're going to choose a coordinate system. Okay. So we're going to start breaking up vectors now, or a vector in this case, right? The idea is, again, the program is that you're ultimately adding up all the forces in a given axis, calling that F net for that axis, and it will equal MA for that axis. Then you go to another axis, you add up all the forces. I mean, you literally just itemize all of the arrows that are in your diagram, and that becomes F net for that axis, which equals MA for that axis. You go one axis at a time is the whole idea here, but we need axes to do that. Right now, we've got like things going like this and things going like this. That's not a clean coordinate system. So we pick a coordinate system, we picture the world, we say, okay, from here on in, this is my x-axis, and therefore anything perpendicular to it is my y-axis. And we make sure that all forces are broken up into components that lie along those axes. Like that's what we're about to do. The first point, though, is how do you choose your coordinate system? Like what is your x-axis? And again, by the way, that's what's tricky in the lab, but I'm trying to build to that. How do you pick your x-axis? Your x as well, according to Galileo, it could be whatever you want. I mean, that's why this all works. You can do physics in whatever coordinate system you want. However, some coordinate systems are a lot more convenient and solvable than others. So the strategy here is that you pick an x-axis, you assign your positive x-axis so that it lines up with the expected direction of positive acceleration. You line up plus x with plus a is the idea here. So that's where the trickiness of the lab comes in a way. But what's happening here is, okay, the problem already told me that even though I'm like pulling this thing like physically like that, the apple is going to accelerate along the table, like say to the right. So I'm going to think of that direction, the horizontal direction, as the x-axis, as you might have anyway. And I'm going to think of up and down as the y-axis. So my coordinate system, it looks like this, as you would expect. So thus, the tension force must be broken up into components. Like any force, any arrow that you see in your picture that's not lined up already with one of the axes has to be broken up. And that's what you're doing in the lab. Now, I'm going to say this again because the whole purpose of I'm trying to get this to the state of your lab. Notice what I'm doing. It sort of seems obvious. Well, actually, I'll just do it and then I'll relate it to the lab or remind me if I don't. But so I'm saying zoom in on the tension force, the string. It looks like this, right? This is the tension force. Well, this goes back to vectors in general, like the last example, like displacement vectors or velocity vectors or any kind of vectors. If something is going, for example, northeast, then that means it's really going some amount east while at the same time going some amount north. That's the whole idea of vectors and vector components. So if I zoom in on the tension, it's 30 newtons at 30 degrees up from the horizontal. Well, what that really means is it's going the apple's being pulled over some amount while it's being pulled up some amount. Specifically, it's being pulled up at t sine of the angle, and it's being pulled over at t cosine of the angle. Like SOHCAHTOA, sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. So, and I'm just trying to keep this. So I'm writing just T sine theta and T cosine theta because I'm saying that would be true. Like it doesn't even matter what the specific numbers are of this yet. The breaking up procedure is what it is. So so I just zoomed in on the tension and said, really, that tension is equivalent to something going like this, to a string pulling up while a string pulls over. So what do I do with that? I substitute back into my diagram. And this is just a mistake people make a lot. Like I'm saying that the one hypotenuse is equivalent to the two legs. Either way, we're expressing the same action. So I go back and revise my free body diagram. I turn it into a component diagram. So I substitute into the component diagram. Here's the component diagram. Wait, let me make this clear. Sorry. What I'm trying to say now is there are now four forces in our free body diagram. It's a free body diagram that's built of components. So there were three forces in it. One of the forces just got broken up into two components. Notice I only draw the two components in here now. The original hypotenuse is gone from the diagram. So I'm saying now we have an object, an apple. This is the apple on the table. It's being pulled down by the earth. It's being shoved up by the table. It's being pulled up somewhat by the string, and it's being pulled over somewhat by the string. Right? That's what this diagram is saying. Four things are happening to the apple. And the reason I've drawn this diagram is now that all those four things are accounted for on my axes. So now I can solve one axis at a time. Right? I'm going to go one axis at a time and apply Newton's second law. And the habit that I'm always going to follow is so there's two axes, the x-axis and the y-axis. The ultimate thing that the question is asking me is what's going on the, sorry. I just saw in the chat, break it down to x. Yes, I'm going to break it down into x and y. Awesome. Yes, Andy, awesome. And one like pro tip or whatever is, since I ultimately care about the x, like the ultimate question is asking what's its acceleration along the x, I always, as a strategy, start with the axis I don't care about. You'll see more and more why that's just a productive habit to be in. Well, there's a number of reasons for it, one of which is sometimes we get information from the earlier axis that we need to apply to the axis that we actually care about. And there are other reasons too. But anyway, so I'm going to go. So yes, I'm going to do what Andy says. I'm going to break it to x and y and solve one at a time. So first, the y-axis. But again, just trust me, always start with the axis that you care about less. You get what I'm saying. All right, so the y-axis. So we say f net, okay, let me be even more specific. Remember the law is this. That's Newton's second law. It's a vector equation. So what it's telling me right from the start is it is true independently yet simultaneously along each axis. So first I go to the y-axis and I say, fine, the sum of all the y forces equals the mass times the acceleration along the y-axis. This is the y-axis. So now I just look at the y-axis and I just put down every single force that's labeled in the y-axis. And all forces going in one direction, I give a positive sign, and all forces going in another direction, I give a negative sign. I'm adding up all the forces. It's always F net, like sum of all the forces. It's just that we're taking into account direction, plus and minus, right? So I'm going to go, so I'll just make this clear. So yeah, so like call up positive and call down negative. Then along the y-axis, just like, well, yeah, along the y-axis, I have I have normal going up. I also have T sine theta going up. And then I have mg going down, right? This is the y-axis. Notice all I'm doing is just taking the arrows from the diagram and putting them right here on the left side of Newton's second law. The whole idea behind all of this is that I'm not even thinking, right? Like once I get used to, I mean, I'm not discouraging you from thinking, but once you really get used to the strict rules for drawing these pictures, the whole goal of all the pictures is by the time you're done with the last picture, it just does the math for you, right? So I've got n plus t sine theta minus mg equals may. And I'm looking at the y-axis right now. What can I say about the y-axis? Well, in the y-axis, the acceleration in the y-axis is 0, right? This thing is just moving horizontally. And by the way, this is one of the reasons that we always line up, we always choose an x-axis to line up with positive acceleration, because if we do that, then automatically the y-axis won't have any acceleration in it. So in other words, the apple is not accelerating up nor crashing through the table. So the right side is 0. And so therefore, the left side equals mg minus t sine theta. In numbers, if we plug in the numbers, we said the mass was 2, acceleration, free fall acceleration is 10. Annie said the tension force was 30 times the sine of the angle is 30, right? So we have 20 minus 15 equals 5 newtons. Now, I haven't finished the problem yet. I'm just noticing something, okay? The ultimate problem was asking how. Notice the weight of the apple here is 20 newtons. And here I just did a calculation on the y-axis to show myself that even though the weight of the apple is 20 newtons, the upward normal force of the table is not 20 newtons. It's a lot less. It's 5 newtons. Why? Because the table is trying to support the duck, but the rope is helping the string. The string is pulling somewhat up. So the table is not supporting the entire weight of the apple. It's supporting some of the apple. The rest is being picked up by the string. That's why literally it says the normal force must equal the weight minus whatever the vertical component of the string is. I can't say it any more specifically than that, but so notice just the normal is 5 newtons. Now, do I need that information? Not necessarily in this problem, but the reason I always go to, so I'm going to finish. I'm going to go to the x-axis now. But if you're paying attention to the lab stuff, you'll realize that if there were friction in this problem, in order to calculate the friction on the x-axis, I would need to know the normal force exerted on the y-axis. So this is, so like pro tip again, back to the lab, the reason I always go to the y-axis first is because I pick up information like the normal force magnitude there that I can then use if there is friction on the x-axis. But anyway, going on, we now go to the x-axis. On the x-axis, the sum of all the x forces equal the mass times the acceleration on the x-axis. So on the x-axis now, there's only one force. It's t cosine theta equals max, right? And now a is not zero. On the x-axis, a is what we're solving for. So it's 30 times cosine of 30 all over 2, right? So it's 15 times the cosine of 30, and the cosine of 30 is like 0.87. Sorry. Um, okay, so the acceleration along the x-axis here would be about 12.9 meters per second squared. Now, so okay, so that's just one example. What I just did was I'm going to keep going. I mean, we have 15 minutes. What I just did was add the layer in effect of, well, first of all, what I just did was show you how this is the procedure. This is how you solve Newton's law problems. System schema, pure free body diagram, component free body diagram, apply F net equals MA, one axis at a time to ultimately solve for A. Like that's a procedure and it works every time, including the lab. It's just obviously things can be more complicated, such as in the lab. The first way in which the lab is complicated is that there's an angle involved. So I've partly just shown you how to do an angle. But let's be, well, but let's be very clear. In the lab, the entire track is angled. Like you're not pulling at some weird angle, the entire track is angled. So how do you deal with that? Well, if you follow strictly the rules that I just said, when you go to choose your coordinate system in the lab, you realize that the whole your block or your marble is accelerating along the inclined plane. Like whether it's going down or it's going up, it's accelerating along the inclined plane. So if you follow the system that I just recommended, you would choose an x-axis that is aligned with that expected direction of acceleration. In other words, you would tilt your whole coordinate system. This is why we do this in the lab. You don't have to, but it is much, much, much more strategic to do this. You tilt your whole coordinate system in your mind. So you make this the x-axis. And just to cut to the chase, that means that the gravity force that seems like it's just pointing straight down, like always, you realize, okay, that is not along an axis. It's gravity that is neither along an x-axis nor along a y-axis. So gravity has to get broken up. It doesn't have to, but that's the thing we do. Rather, here the tension force got broken up, but over there gravity will get broken up. But it's the same logic always in physics is you choose a coordinate system for which the x-axis lines up with acceleration, and anything that's not along the x-axis or the y-axis gets broken up. And then you do this procedure. Okay, so that's number one. But number two, the other thing that's missing from this that I have to add now with 14 minutes is what's the deal with friction? right? Okay. So this is like, okay. What I'm adding here, and I am aware of the time, I'm saying here's the new layer that we're gonna add some problem now. Say it's all the same situation as it was a second ago. So I'm redrawing. Say we have this table. Whoops, sorry. We have this table with this apple, right? And still, let's say it's being pulled up at an angle. God, sorry. Right? But let's say now, the table's actually rough. It's realistic. It's rough. And what and its roughness is identified, let's say, by what we call the coefficient of friction, specifically the coefficient of kinetic friction, or some people call it the coefficient of sliding friction. Let's say the roughness is identified by this number called mu sub k. And let's say in this example that number is 0.1. Like now I want to resolve the problem. I want, once again, I want to solve for a sub x. And along the way, I want to note what the normal force equals. Okay, now again, I might run out of time here, but so we're adding the layer of friction now. How does friction work? What is this coefficient of roughness idea? Remember that friction is part of a phenomenon when two rough surfaces push against each other. The whole idea of friction is that the more two rough surfaces go like this, the harder it is for them to go like that, right? The whole idea of friction is by pressing. If a surface is actually rough, if you look at it sort of microscopically, if a surface is actually rough, the more it presses, the more it locks into the other surface like teeth of a comb, and the more difficult it is to rub or slide along, right? So there's two contributing factors to friction. The friction force that specifically, technically, the kinetic friction force that one surface exerts on another to make it more difficult for the other to slide or rub against it. The kinetic friction force from here on in is the roughness for sliding times the normal force between the two. What I'm saying is there's two contributing factors to friction: how rough the surfaces are and how hard they're pressing against each other. As either one increases, the whole package of friction increases. What is mu? Mu is a number that just ranges usually from 0 to 1. It's a coefficient. The units of mu I'm saying mu is a pure number. It's literally a pure number because what it is a ratio of how much friction force you get per each Newton of normal force. It's saying no, that's what it is. So it's Newtons divided by Newtons. The rougher something is, the more sliding resistance you get per each Newton of pressure of surface contact. So in order to calculate the friction, you always need to first calculate the normal force. So in this case, so we've got 7 minutes. So, but this is a memorizer. If you and this is what you're using in the lab. Like I'm saying, from now on, the friction force of sliding or of okay, actually, I'm going to make this even more clear. So I'm basically saying really quickly, with 6 minutes left, there's really two cases of friction. Okay, there's two cases of friction. One is the one that the two cases of friction are static friction or kinetic friction. Kinetic friction is when one object is sliding or moving. Kinetic means motion. So kinetic friction means when one is actually sliding relative to the other. That is the case that I'm doing right here, and that's the case of the lab, when you actually have motion between the two objects. But just to be clear and for the record, the objects could be not moving relative to each other, but something could be trying to move. Like when I try to pull something across my desk and I have to pull really hard to get it to move, what's holding it in place is called static friction. It works almost the exact same way, the math and everything, but it's a different coefficient. I'm just trying to be honest and thorough right now. So every surface really has two different coefficients. One for the sliding case, which is what we're concerned about here, versus the other coefficient for the stuck case, the static case, okay? Right now, but for the lab and everything, I'm talking about this first equation, FK. So both of those you can memorize if you want. But so here, how do we do this? So how do we solve? How do we solve with, well, it's all about just incorporating that new equation that I just gave you. How do we solve with friction? We follow all the same steps that we just did before. System schema, pure free body diagram, component diagram. And then, and when it comes time So I'm going to do that right now. So I'm going to skip all the way to the component diagram because we've already done all the steps already. So I'm going to skip straight now to the component free body diagram that we now have. In other words, we still have mg. We still have the normal force of the table. Sorry, mg. We still have the upward force of the string. We still have the rightward force of the string, but now we have friction trying to hold this thing back. If the thing is trying to move to the right or is moving to the right from the string, then friction is resisting it, slowing down to the left. So we now have friction is added to the diagram, right? Again, this is looking more and more like the lab now, hopefully. So if I want to get the acceleration of this object in the horizontal axis, I do the same thing as before. And again, this is really like what anyway, I look at the y-axis, I'll cut straight to the chase. The y-axis is t sine theta plus normal minus mg equals may, and a is 0. So the normal force, just like before, equals mg minus t sine theta. So the normal force, just like before, is 5 newtons. Now, why do I care? Now I care because when I go to the x-axis with 2 minutes left, when I go to the x-axis, in the x-axis, it's now t cosine theta to the right minus friction to the left equals ma. And what is friction now? Friction is mu times the normal, always. Right, it's this number. So the roughness number is just the roughness. It's a coefficient that multiplies whatever the pressure is that we got from the other axis. So that's why we always go one axis at a time. So now t cosine theta is now oh, did I? Oh, and I realized I made it. Yeah, okay. Sorry. So this is like 12.9 minus 0.1 times 5 equals 2 times AX. So now it's going to be 12.4 equals 2 times A. So A equals 6.4 meters per second squared. In other words, that I know I did that quickly, and it's 1205. But the bottom line is once friction's involved, friction is mu times the normal. So it requires you to get the normal force from the other axis. And especially in the lab, you've got to get the normal force from the other axis. It's not a memorizer. It's not a formula. You get it by solving Newton's laws, Newton's second law, one axis at a time. Hopefully that's helpful. All right, I'm going to stop the recording. If there's any quick questions, I'm happy to answer them. The other class is coming in, so bear with me, but I'm here. Thank you. Thank you very much.